Okay, so we want to look at taking derivatives of vector valued functions, and this is a pretty straightforward idea. So if the vector valued function r of t exists, its derivative, so the derivative of r with respect to t is, we're going to call that r prime of t, is just the limit as h approaches 0 of the vector valued function of t plus h minus the vector valued function at t all over h. Okay, so that's how we do the definition. The problem is that's not very computable, but recall that oftentimes we view r of t as being like some f of t here and then some g of t here. So if you're going to actually just compute that, r prime of t is done component-wise. So it's just going to be f prime of t, g prime of t, right? So like, let me give you an example. I wrote the example in vector form just to kind of keep up with that a little bit. So if I have 1 plus t cubed times I, so that's the first component, plus t, oops, that's not a t, t e to the negative t j, right? T e to the negative t vector j. Then we're going to take a derivative here, right? So this is r of t, r prime of t will then be, let's see, this one's just going to go to 3t squared I, right? And this one is first times the derivative of the second plus second times the derivative of the first. And all of this is times the j vector. So this is going to give me 3t squared I vector plus, and I can do a little bit of rearranging here. I think I get, let's see, this is going to be e to the negative t. I can pull that out. That leaves me with, what's that, 1 minus t times the j vector. Okay, so there's my derivative, right? So the first component of the derivative is 3t squared. The second component of the derivative is e to the negative t, 1 minus t. All right, so that's not so bad. We can establish a couple of simple rules here that should be helpful. So we're going to find 4 rules for vector valued function derivatives. Right, the first one is like a sum or difference rule, which says that if you take the derivative with respect to t of the sum of or difference of u and v, then you just get the sum of the derivatives, right? So it's going to be u prime t plus or minus v prime t, depending if it's a sum or a difference. Okay, so that works the same way. Earlier we said that if you have some constant times a function, right? So now we're going to make it a vector valued function. You can carry that constant and it will have no bearing other than just to kind of move along as a scalar through the process. Okay. What happens if I multiply a regular real valued function times a vector valued function and try to take the derivative? Well, you get derivative of the first times the second plus the first times the derivative of the second. So it's just the product rule, right? So that's pretty straightforward. Nothing unexpected there. And finally, number 4, what if I compose a vector valued function with a real valued function? Well, that's just going to be our chain rule. So you take the derivative of the vector valued function and keep the real valued function and then multiply that by the derivative of the real valued function. So that just functions as a chain rule. Kind of pulls right through. Nothing surprising there. okay, so where this differs a little bit from thinking about just two parametric equations slammed into a single function is it's actually like the meaning of this. Okay, so these things are usually used to describe a particle moving through the plane. So if this vector, and now I'm going to call it x and y because it's pretty specific that this is a particle moving through the plane, is a x function and a y function, and if this is a position vector, then our prime of t, which would be x prime of t, y prime of t, is the velocity vector. Aha, so we're making sense of particle motion here. If I take the magnitude of the velocity, which would be the square root of x prime of t squared plus y prime of t squared, if I do that, this thing is what we call the speed of the particle. So this is actually going to give me back a number. That's the speed. And finally, if I were to take the second derivative with respect to t, I would get x double prime of t, y double prime of t. And this is now the acceleration vector for the particle at time t. So usually when we're using vector valued functions, we're describing some sort of space curve in the plane using as if it's like some particle moving through space here. And these are the relevant quantities that go with that. All right, so let's work an example here kind of simply. Let's say I have the vector valued function as a position vector where I have t minus 2 is the x is controlling the x and t squared plus 1 is controlling the y. Okay, and I want to evaluate this when t is equal to 2. So let's look at r prime of t. Right, so that's just going to give me, what is this, 1 and 2t, which means that this is my velocity vector, and like no matter what time I'm at, the x is always changing by 1 unit per second. It's going to the right, and the but the y is changing according to the time. It's getting faster as time goes on. So this is going to be like some sort of parabola going upward here. So at time 2, this vector is 1, 4, right? So at time 2, every time it's going 1 to the right, it's going up 4, right? The speed at that time 2, right, should be the square root of 1 squared plus 4 squared, which is the square root of, let's see, that's 16, 17, which is approximately 4.123. So this thing is moving at slightly more than 4 units per second. That's its speed. Okay, so this kind of gives you an idea of like how we're actually describing a particle that's moving in space, and this is one of the big reasons why we use vector valued functions.